Okay, so I've had zero success this week with the people at the technical people at Brightspace. They don't seem to understand what the problem is, much less be able to fix it. One of them told me that there's two ways of downloading files, and I must be using the wrong one. And another one tried to tell me that it's easy to turn my files into PDF. I don't know if they're even reading my questions. I don't see this getting fixed anytime soon, if ever. So that's why I went ahead and sent everybody a set of spreadsheets. What I'm going to do, let me just quickly go in there and look at it again. Whoops, no, not that. The Brightspace, because somebody just sent me an email with a suggestion, and I want to check this out. All right, here we go. So this week should be week 7. Yeah, because there's only tonight and next week, and we're done. So this is considered to be week 7. So the Greek examples here, this is an Excel spreadsheet, or it's supposed to be, and this is the mess that they turned it into. So I had a suggestion in my inbox. I just saw it a second ago, so I didn't get a chance to really read it carefully. That somebody says they found a way of doing it. I really want to investigate this because, like I said, I don't think those people are ever going to figure it out. It says here, if you download the document from the cloud, okay, already I have no idea what that means. Okay, oh, there's a picture of a, huh. All right, so let's go back to Zoom. Not Zoom, Brightspace. So what I've been doing, this is what I've been doing. It says here, add existing. And then it says, what would you like to add? And so you notice how it's asking you, say, listen, anything you want, just slide it over here, and there you go. Fine. So that's what I've been doing. If that's not the correct way to go, then they were supposed to tell me that. So apparently, there's a second way of loading everything up. All right, as soon as this thing wakes up, we'll try the second approach. The scary thing is that before the semester, I used this all the time last summer, and I never had a problem like this. This is something that's new. So, this red thing, no. So what am I supposed to be seeing here? Is there like a cloud here? No, no. As far as I can tell, this is the only option that I have for downloading stuff. No. All right. Well, if there's another way of doing this, they like they tried to claim that there is, and then they didn't bother to tell me what it was. Okay. So, all right, let's go back to week 6. Oh, well, of course, all these spreadsheets are unusable now, but let's open up the assignment. Okay, so first we have 15 fill-in questions. These you can get straight out of the slides. You don't have to do any actual calculations with these. Now here we've got two questions. First, you're being asked to price a European call with the Black-Scholes model. Although it doesn't explicitly say that, as soon as you see that it's European, that means you can go ahead and use Black-Scholes. So the template for this, you might as well use Black-Scholes example number 2. It's the more general one. The first one only works if there's no cash flows. So that would be here. Let's get it open. So let's say you decide, you obviously open it up and save it with a new name on it. No, this is last week. This is week 7. Yeah, I'm showing you week 6 assignment. 2 weeks ago, we didn't have an assignment. In week 5, there wasn't anything. It was just a session. So week 6, last week, we did the Black-Scholes and the binomial option pricing model. So this week we're doing 7, which is the Greeks, and then next week we're going to wrap it up with value at risk. But anyway, so if you go,
I was wondering if I could just talk, might be easier. I thought we had to do something on those spreadsheets that you sent over to us.
no, those are just for illustration. All you had to do is take the Black-Scholes template. Like, for example, here it is. And basically, you just replace these numbers. Oh, what the hell happened here? Oh, here it is. It's on slide 2. Okay. So in other words, if you see how these are already set up to calculate whatever results you need. From this point down, these are calculations that are being done in the spreadsheet. You just enter these numbers. So in other words, if you look at, that's not it, sorry. Now I've lost it. Assignment number 6 was floating around here somewhere, and I've lost it.
There was a spreadsheet with a bunch of numbers like 1.95 and some decimals. I didn't know what those numbers meant. It was like one of the spreadsheets that was attached to that email.
Yeah, I sent out a whole slew of spreadsheets because, you know, the Brightspace isn't working correctly. But the assignment for 6 just involved the Black-Scholes model. All right, now, of course, I can't find the assignment again. Let's get it open one more time.
I think I know which one you mean. I just didn't know which numbers to plug in where. I think that's what it was about.
Hi, is this assignment due today?
Yes, it's supposed to be due today.
Okay, this wasn't sure why you're going. Okay, no, okay, no worries.
Yeah, this is the one that was due today.
Okay, got it. Yeah, got it. Thanks.
It looks like this thing is offering to download this as PDF again. It's like it just never ends with this PDF crap. See now, yeah, this is the assignment, and it actually is a Word document. I'm just downloading another copy of it so I can show it to you. So if you look at this thing, again, there's 15 questions, fill-ins that you can do based on the slides. And then, so here we go. So using this as a template, 9 months means 3/4 of a year. So you replace T with 0.75. And then strike price is 150. That goes there. The risk-free rate is 2%. That goes here. The volatility is 20%. That's here. And the price of the stock is 165. So if you plug those in, actually, I can do that right now without changing this. 165. The strike is 150. The risk-free rate is 2. This is 0.2, and the time it's 3/4 of a year. So it's already done. There it is. $18.78 is the Black-Scholes price of the European call, and either based on put call parity or the other formula that we use down here, which somehow got mangled here. Your put price would be about 522. So that's all you had to do. So you're basically using this as a calculator. I figure, I mean, that's, you know, it doesn't need to be any more complicated than that. So most of the work will come from these fill-ins. And, you know, there's a fairly good representative selection. So if you can do these, that means you really do understand what we've been doing. So I didn't ask any questions about the binomial option pricing model because it's just too complicated. I mean, I guess I could have, but I thought it would be a bit much since, you know, it's a very complicated topic. So I just wanted to introduce it to you, to get a sense of what exactly is this model doing and why is it possible to price American options with it. And again, because it gives you the ability to stop at each point in time and consider whether you should exercise early or not. Black-Scholes doesn't give you that ability because of the way it's structured. It doesn't actually consider the price of the option at intermediate times. It only considers the price today and where the underlying asset will be in the future. So it's creating a probability distribution for the stock in the future and using that information to figure out what the option is worth today. But it doesn't give you any insights into what's happening along the way. Whereas the binomial option pricing model is explicitly showing you the path that the stock is following. And so it becomes possible to stop at each node and say, listen, should I exercise early or not? So that's why the binomial model can be used for American options, whereas the Black-Scholes cannot. Now, the binomial model is designed to follow the exact same assumptions of the Black-Scholes model. So you can tell whether your binomial model has been set up correctly. If you have enough time steps, it should price European options exactly the same way as Black-Scholes. If not, you have a problem. So that's called calibrating your model, where you take the model and make sure it works correctly for a known result, and then you apply it to something where we don't actually know what the price is. So anyway, so yes, you can read more about that in Hall's book. He has a lot of discussion about all of these topics. It's a very, like I said, a very deep, complex book. And he takes all of these subjects that we just had time to start and goes deeply into each one. And there's also a lot of chapters in that book. So if you really want to pursue this further, you should continue to read Hall's book because it's so well done. The one thing he doesn't do, which is kind of a problem for me, is that he doesn't actually show you how to implement these models in the computer. He has his own software and all, but he doesn't say, well, here's the steps you would follow to do this in Excel, let's say. That could really add a lot of value to that book, in my opinion, but he doesn't seem to be interested. So we do what we can here. So anyway, also the next 2 weeks, there won't be any more assignments. We're done with assignments. You know, from here on, it's just let's learn the new material and then and let it go with that. I think that's plenty of work we've done so far. And there's no exams either. Again, because of the complexity of this material, it wouldn't really make any sense. So anyway, so why don't we start with the Greeks? So the Greeks are a very different subject because what you're really trying to do is understand how different factors affect the price of an option. And this is very useful for traders. And it also gives us insights into how options work. So hold on a second. Let me open up the notes. So remember, this is week 7. All we have is the PowerPoint slides and this spreadsheet called the Greeks examples number 1. So I emailed that to everyone. I hope you got them, because as we know, the Brightspace is completely useless when it comes to spreadsheets. And the IT people are just, you can tell there's a problem when they're clearly not even understanding what you're telling them. And then they try to guess and they give you all this bunch of crap. And then it just, anyway, I'll have that out with them later on. Anyway, so here's the Greeks. Now the name, the Greeks, you'll see why they're called the Greeks in a minute, but here's what we're going to do. We're going to look at these risk measures. And they're collectively known as the Greeks. We're going to see how to calculate them. We're going to learn how to interpret them and see how they're used for hedging risk in a portfolio. Now, just as a recap of what we've seen before, the price of an option, whether it's a call or put, depends on several underlying variables, including the price of the asset, strike price, volatility of the underlying asset, which tells us how much the price changes over time. It is measured specifically as the standard deviation of the returns to that asset, the risk-free rate of interest, and the time until the option matures. Now, not all of these have the same impact on an option's price. And in many cases, the impact depends on whether the option is a call or a put. So if any of these variables changes except for the strike price, then it'll impact the price of the option. Okay, because clearly the strike price is a fixed constant. So now the reason why they're called the Greeks is because the names somehow were associated or assigned delta, gamma, theta, vega, and rho. Now, it turns out, ironically enough, that vega is not actually a Greek letter. Somebody slipped up there. So that measure is sometimes called lambda, so that we have a symbol that we can use to represent it on paper. By the way, just before we get any further, I just want to show you that these are the most standard ones, but there's many others. Let me just show you what I'm referring to here. There's an article on Wikipedia that has, oh God, I think I mean actual Greeks. Yeah, here we go. This should be the one. What they've done is they've got, here it is. This is what I was hoping for. This is the chart. And so many of these are very obscure Greeks. You don't see them used very often. The ones we're looking at are basically these first three, the gamma, and God, where's the other one? Missing, I can't find it. Wait a minute. Delta, gamma. Oh, they're missing. For some reason, they're not showing rho in here. I didn't notice that the first time. But anyway, these others are kind of strange with very oddball names that are dreamed up later on. These are often functions of other Greeks. They're not directly related to the options. For example, this Vanna, whatever that is the sensitivity of the delta to changes in the volatility. So you can see that these are getting a little further and further removed from the actual option, but the ones we'll be focusing on are these top three, and then the gamma, plus the one that represents the sensitivity of interest rates, which we call rho. So anyway, so it's so funny about this vega. I guess somebody thought it would be cool to call it vega because it starts with a V. And now, but it isn't even a Greek letter. So we sometimes see it called lambda. Anyway, so now numerically, we can calculate all of these by looking at the Black-Scholes formula. Let's go back and look at it real fast. So the formulas that I'll show you tonight are basically derived in the following way. We go back to the original Black-Scholes formula. Okay, where is it? Okay, here we go. So we'll go back to the Black-Scholes formula. Here it is. And what we're basically doing is taking derivatives of this formula with respect to the different variables in that formula. In other words, the first one, which we call delta. Now I lost my place. There it is. The delta is basically a measure of how sensitive the calls price is to changes in the asset price. So basically what somebody did was they took the derivative of this call price with respect to S. And so the result is that the delta, at least for this case, is ND1. And that's where it comes from. It's the sensitivity of the call price in the Black-Scholes model to changes in the stock price or asset price. And then we also have gamma, which we'll get to in a few minutes, theta, lambda, and rho. Now, by far the most widely used of these is delta. So think of it as the change in the call price when there's a change in the underlying asset price. So for example, actually, you know what, let's do this. Oh, here we go. So in this Greeks example sheet, what I did was I copied the example from the second Black-Scholes from last week. So the reason why I did that is so we can see as an experiment what happens if I change the stock price. Okay, so this is an example we had from last week. And I called it Black-Scholes number 2, I believe. Here it is. Let's get that thing open. Okay. Oh, it's not. No, it's not the same exact thing. It's this other one. Sorry, it's this one. There we go. Okay, it's this example. This is Black-Scholes number 1. Okay, now, so what I wanted to do is take that as a starting point and then experiment with it basically. And so we've the delta in this case, as we'll see why this is the case, is 0.6359, which indicates that if I raise the stock price by $1, the stock price by $1, the option price should go up by about 63.59 cents. Okay, so we can try this by making a little table here. If the stock price is, let's say, 52, the call price is 7.633. If the stock price goes up to 53, then let's see what happens. Now, according to this spreadsheet, the Black-Scholes price will go up to 8.2808. Okay, now, so what I'm going to do is calculate the difference. So there's been a $1 increase in the price of the stock, and the change in the price of the call is about 64.78 cents. So you can see it's not a perfect estimate. The actual change is about 64.78 cents when the, oh, you know what I should have done? Hold on. If you noticed that when I changed the stock price, the delta changed as well. So what I'm going to do right now is copy down the deltas so that we don't have that problem again. And then when I change it to 53, if you notice the delta does change, it goes up to 65.94. And that proves to be very significant. The actual delta itself is changing. It's not just the stock, the call price. Now, what I would like to do is show you exactly what's going on here with a diagram that we're all very familiar with. So here's what we're seeing. You recall that when we're looking at a call, I might as well change the color here. So there's the payoff. And here's the strike price, which we'll call it K. So you might recall that the market price is derived by this curve. And so as long as the expiration date hasn't arrived yet, this curve is actually giving us the market price. The payoff is the so-called intrinsic value, which means that if the price falls below that, there would be an arbitrage. But anytime before that, the market price will be higher, and the differences we've seen between the two curves is referred to as the option's time value. Okay, so in other words, the stock price is, let's say, I'll call it S star or something like that. At that stock price, the market price of this option is significantly higher than the payoff, which means that it has a lot of time value. But as far as the delta is concerned, the delta is actually the slope of this curve. So what I'm going to do is draw a series of these little tangent lines. If you recall from your math travels, the slope of the curve can be defined as the slope of these tangent lines. And if you look at it carefully, you'll see that this first point here, the slope is close to 0. Up here, the slope is close to 1. Right about here at the money, it should be right around 1/2. I may not have drawn this very well, but the slope right about there is going to be very close to 1/2. Okay, so in other words, as we move further to the right, as S increases, the delta rises from nearly 0 to just about 1. It's not exactly, it's getting close. It will only achieve 0 or 1 when the expiration date arrives. Because if you look at the payoff profile, the slope here, when the option's out of the money, is exactly 0. And up here, when the option's in the money, the slope is exactly 1. Okay, so at any other time, besides the maturity date, the slope of this price curve will be somewhere in between. Okay, if the option is very deeply out of the money, which it is below K, remember this is out of the money, the delta will be very low. When we get up here into the in the money territory, the delta is getting closer and closer to 1. Okay, so in our example, the delta is over 1/2 because this option is $2. Well, in this now it's $3 in the money, but it's slightly in the money. If this was exactly 50, let's see what happened. It should be really close to 1/2. See, well, it's a little higher, but that's because there's a lot of time value here. If we reduce the time value, let's say to 0.3 or something like that, then this delta is going to get closer and closer to 1/2. And in fact, when the time is 0, we don't want that. Close to 0, it's getting really close to 1/2. Okay. All right, let's get these back to the original values. Okay, so we can experiment with the properties of this delta just by changing the values in our spreadsheet. Okay, but ultimately, this is what we're doing. Okay, so again, you've got the red line is the payoff profile, the intrinsic value. That is only true of the options price on the maturity date. Anytime before that, this black line is the market price, which, as you know, gets closer and closer to the red line as time elapses. The delta of the option depends on the stock price in such a way that with low stock prices, we have a low delta. With high stock prices, we have a high delta. But it's not going to ever go above 1 or below 0. Okay, cannot go outside that range. So, and at the money, we're going to be close to a half, especially as time elapses. Now, how do we calculate it? That's again the derivative of the Black-Scholes model. So we'll see in the slides that the actual calculation. Oh, I see. I've already done something like that in the slides. Here with 53, we've got $4 of time value. And yes, I've drawn in the little tangent line so you can see the delta is nothing but the slope of this curve at those points. Yeah, okay, well, all right, so none of this is completely new because I just got through showing it to you. But what we do want to know is how is this actually calculated? So this is a derivative of the Black-Scholes model, and it turns out that it is nothing but ND1. Okay, so if you come back here, if you notice, it's not a coincidence that the delta of the call and ND1 are the same number, because they're the same thing. And that comes from applying calculus to the Black-Scholes formula. You're taking the derivative of that function with respect to S, and this is the result. So the ND1 term is the delta of the call option. Okay. Now that proves to be one of the more useful of the Greeks, probably the most important one, because if you own options, you want to know what's going to happen to their value if the stock price changes. Because at any given time, you might decide to sell them. Or else, if you're hedging, you may decide that maybe you should buy more options or maybe sell some of them to improve your hedging position. Because the awkward part about hedging is that, unlike with a forward contract where you're locking in a position and that's the end of it, with an option, your position can actually gain or lose value even if it's hedged. Okay, so you have to really keep an eye on these Greeks, because that will let us know what's happening to the value of our position when they're given changes in the marketplace. And also, unlike a forward contract, it's completely driven by the value of the underlying asset and the time until the maturity date. That's it. Okay. Here we've got many factors that can influence the value of the option. So hedging with options is a little bit trickier. Okay, they're very powerful and flexible, but these values can change very quickly as well. Okay. So anyway, that's delta. Now we're going to designate the delta to make sure we know which is which. We're going to use the subscript C. Delta C, just to make sure we know that this refers to the delta of a call option, not a put option. And as we've already seen, based on the graph that we drew right here, knowing that the delta is the slope of that curve, we can make the statement that the call delta can never fall outside the range from 0 to 1. Okay. Now, this is not a situation where an arbitrage can take place. What it means is that it's not mathematically possible for this delta to fall outside this range. Okay, so it's, we get used to thinking about everything in terms of arbitrage, but here it just means that mathematically it's not possible for this to happen. So when a trader chooses which options to use to hedge his position, this is going to be one of the first things that he looks at. Okay, what is the delta? And in fact, there's a very widely used strategy in the options markets where what you can actually do, let me add this to this document here. One strategy that is employed in the options markets is to create a delta neutral portfolio. Okay, so let's just say that, for example, suppose that a portfolio, just to keep it incredibly simple, consists of 100 shares of Apple stock. Now, what's interesting here is that if you look at the way delta is defined, let's see where it is listed here as the change in the call price divided by the change in the asset price. If you a more formal way of writing this in mathematics is to do this, but it means the same thing. Now, you may have seen these symbols before, maybe not. This is math for the partial derivative of C with respect to S. Now, what exactly is that all about? When you see that little special symbol, partial, that means that you're holding everything else constant. Everything else that could conceivably affect the price of the call, we're assuming that it is going to stay constant, and we're going to assume that only the asset price changes. So because there's so many other factors that can affect the call price, we basically have to be clear that we're assuming that only the asset price is changing, everything else is being held constant. And so that's known as a partial derivative. And it means the same thing as the change in the call price with respect to the asset price, but with the understanding that we're holding everything else constant. All right, that's a huge deal. It's everything else is being held constant. Anyway, so then what we're going to do here is, if you take this definition, what you'll see is something very interesting. I'm going to copy that if it ever wakes up. Okay, let's give it a minute. Yes. So I'm going to ask myself the following question. Could we define delta for the underlying asset? Okay, so we could think of it as, let's say, delta S for the stock. Well, then here's what would happen. Delta S would mean change in the asset price over the change in the asset price. Well, that's interesting, which means that by definition, this delta is automatically equal to 1. Okay, so therefore, a portfolio with 100 shares of Apple stock has a total delta of 100. Okay, so how can this be hedged with call options? Okay, so let's assume that each call has a delta, just to keep it simple, of 0.5. This means that we would need 100 over 0.5 okay, equals 200 call options to completely eliminate all the risk in this portfolio, because the total delta would then be 0. Okay, in other words, on the Apple stock delta. Oh, wait a minute. I just realized I'm sorry, I messed this up. We would need to sell. No, we wouldn't, sorry. We need to buy puts. Yeah, I'll tell you what, let's save this example for a little bit later. I just realized we need to do this with respect to puts because calls will not hedge this position. unless you sell them. Yeah. Okay, so all right, I'll tell you what, let's save this example for later, but because I just realized I'm doing it in the wrong direction. So a portfolio with 100 shares. So the key here is that the Apple stock has a delta of 1, so 100 shares would have a delta of 100. A call option has a positive delta, but if we sell the call option, the delta becomes negative. Okay, just keep that in mind. So we'll do another example later on. What I really want to do is bring together these stocks, not with a call option, but put options. So when we discuss put options, we'll come back and revisit this example. But the key detail here is that we can, if we do this correctly, create what's called a delta neutral portfolio. This portfolio has a delta of 0 so that its value won't change no matter what happens to the stock price. Okay, in other words, if we have created a delta neutral portfolio with options, that means no matter what happens to Apple stock, the value of the portfolio will be exactly the same. In other words, gains to the Apple stock will be exactly offset by losses to the options and vice versa. So a delta neutral portfolio is set up when we have no idea what to expect in the market and we want to, let's say, eliminate all of our risk without necessarily selling the stocks. Oh, only for short periods of time. Let's say that the market is coming into a very rough period where nobody knows what to expect. Something terrible is going on in the world, and we are afraid that for the next couple of weeks, the markets are going to be in a lot of turmoil. So rather than selling our stocks, we may want to instead put up this position. Once the danger is over, we would definitely unload this position, this options position, because you're right. If we don't have any delta, we can't make any money. The price, it would just, the portfolio value would never change. So this is meant to be a very temporary approach. It might only last overnight, for example, or maybe we're concerned about what the Fed is going to do at its meeting tomorrow. And so for the time being, we'll just hedge our position so that no matter what happens to interest rates, we will stay in the same position. Or maybe we're afraid that Apple's going to make a very scary announcement next week that they've been thrown out of China, let's say, and they can't manufacture anything there anymore. Something is going on, and we don't want any risk at all. It depends. It depends on what our big picture plans are. It may be that there's a restriction on the stocks that maybe we're not allowed to sell them, or maybe there's other possible reasons why we might do this instead of, selling the stocks. But the thing is, once you buy the stock options, you may be able to sell them at a profit when this situation is over. So the cost of buying the options may not be all that expensive. It depends on what our strategy is. If we buy the options and hold them to maturity, it could get very expensive. But if we're planning on unwinding our position very quickly, we may end up, getting all of our money back when we sell the options. So these strategies may only be for very short periods of time. A good example of this would be, let's say you are an insurance company. And insurance companies do invest a lot of their money in bonds, okay, very high quality bonds. But even then, sometimes the markets go into rough patches, and even high quality bonds can lose money if interest rates move in the wrong direction. So they are in a position where they can only really invest in safe assets, but they don't want a lot of turnover in their portfolios. So what they may do is set up these temporary hedges just to make sure that while this rough period is coming up, that we are hedged, and then we can unwind all of our positions if necessary. Now, of course, it's also possible that you can gamble with your options, and by taking exposure to delta. But if you're hedging, usually the purpose of hedging is to reduce the delta of your portfolio, not necessarily all the way to zero, but certainly to reduce it below where it is now, if you're not in a position to sell your assets. So, think of these as potentially very short-term transactions. All right, anyway, where were we? So I think we now want to introduce the puts and see how they work. Okay, now with the puts, now as you can probably imagine, everything's going to work well. The put, because remember what's happening here, when the asset price goes up, the put value actually goes down and vice versa. So unlike the call, where the delta will be between 0 and 1, here the put delta is going to be negative. And it is bounded, as you can probably guess, between 0 and -1. Okay, so in other words, the delta of a put cannot fall below 0, but it also can't go above 0, but it can't fall below -1 either. And again, it's the same reasoning. If you look at this graph where we have the intrinsic value or payoff to our put, and the red line is the market price, that red curve has a negative slope. And when the option is deeply in the money down here, the put delta is going to get very close to -1. And when the option is out of the money, it's going to get very close to 0. And in between, similarly to the call, if we're right at the money, it's going to be right around -0.5. Okay, so the sign is different for the call and the put deltas, because they're affected differently by the same changes in the stock prices. Okay, so the calculations there are also taken from the Black-Scholes model. And now actually, here's a shortcut. It turns out that if you already know the call delta, you don't need to calculate the put delta separately, because all you have to do is take the call delta and subtract 1. Okay, so if you already know the call's delta, you subtract 1, and what's left is the put delta. We'll see why in a second. And by the way, I just want to remind you that because delta C, the call delta, is nothing but our old friend ND1 from the Black-Scholes model, that means that delta P could be also calculated as ND1 minus 1. Okay, so when it comes time to actually calculating it, what you can just simply do is take your ND1 and subtract 1, and what's left is your delta for your put. It may be that that is the reason, because for hedging strategies, they may be more useful than the ones that are deeply in or out of the money. A lot of the hedging is going to take place with the calls and puts that are close to the money. But yeah, I mean, I am sure that has something to do with it because a lot of the trading volume is for hedging rather than speculation. So, I mean, the purpose of the calls in the first place is to hedge. Now we know people are hedging or speculating out there, but the ones that are the most useful for hedging strategies definitely will have the highest trading volumes, which you would imagine is very close to the money. The ones at the other extremes are good for certain types of strategies. For example, if you're worried about the market crashing, you might find yourself buying puts that are very deeply out of the money, because they're going to be very, very cheap but they provide you with protection from a huge decline in the market. So when people are very nervous, the prices of those out of the money puts start to rise and their trading volume goes up. But when times are good, people hardly pay any attention to those puts and their prices are very, very low. Okay. So that would be an example when the demand for an option can depend on the strike and also what's happening in the marketplace. Yes, that's right. And so sometimes you need a specific delta to implement your strategy. So, and so when you look at the chart of available options, the chart doesn't show you the deltas, but it does show the strike prices. And you can see the deltas are directly related to those strike prices. And so if there's a huge demand for at the money calls, that means, there'll be more volume in those options that are right at the money. All right, now, so there's a brief derivation here. I don't know how important this is, which explains why this is true. Maybe let's kind of skip over that. You can look at it if you're interested. But for the example we've been looking at, we know that the call delta is 0.6359 because that's ND1. And so here, all I did was I took this number and subtracted 1. And so the corresponding put delta is negative 0.3641, which means that if the stock price goes up by $1, the price of the put should go down by 36.41 cents. Now we know that it won't be exact, but it'll be fairly close to that. Okay, so that's how they're related to each other. Now, I think I do have some graphs in here that, here we go. This is what I was looking for. Imagine yourself taking this example and changing the stock price $1 at a time, and then recalculating the delta for the call. Then you plot this on a graph. What would it look like? Well, I'm glad you asked because it's right here. So what you're seeing here in this graph is on the horizontal axis of the stock price. On the vertical axis is the delta of a call. And so here, exactly what I mentioned is happening. What we're doing is trying all the different stock prices and calculating the corresponding deltas. And if you notice, of course, the delta is increasing as we saw when we first did this. As we move from left to right, we can see the slopes are increasing, but it's not that obvious how quickly they're increasing. What's happening is that at first the deltas are increasing very slowly. Then they start to accelerate. And of course, as you know, when we reach, in this case, the strike is $50, we should have a delta of around 0.5. And then after that, the rate of increase starts to tail off. You notice how the curve is flattening off. And eventually, though, it will reach 1 or get very close to 1. So we sometimes call this an S curve because of the way it starts to go up slowly and then it starts to accelerate and then it starts to slow down again. And so we have this unique shape which shows us the relationship between the stock price and the delta. Now, here's an interesting result. We've already seen that the delta of a call -1 gives us the delta of the same put. Okay, so let's go back and revisit that for a second. The difference between these two is I took the call delta, subtracted 1, and I got my put delta. So they only differ by a constant. And so that tells me that this curve for the put will be the same shape, except that the numbers are all negative. And in fact, that's exactly what we see. Whoops, there you go. Now, if you look at these carefully, you'll see it's the same S curve, except the top or upper bound for the put delta is 0, the bottom is -1. Okay, so as the option is deeply in the money, as we move to the right and move further out of the money, the delta is becoming less negative or increasing. Right at the money, it should be -0.5. And then as we move up and up and up in the stock price, we're moving further and further out of the money, and the delta is going to be very small. So the two of them behave in a very similar way. The main difference between them is their signs. They both respond in a similar way to changes in the underlying asset price. Anyway, so now that we know that, we can come back to this example that I started to do, and I did not do it correctly. The delta neutral portfolio. So here we go again. We have 100 shares with a delta of 100. Suppose that we can buy a put on Apple stock with a delta of -0.5. Then if we buy 100 over -0.5. Now the negative just means that it's a put. So I'm not actually going to divide by the point, by the negative. So the total delta of these puts will be -100. That's the key to the whole thing. 100, we bought 200 puts, each with a delta of -0.5. So therefore, we have a total delta of -100. So the portfolio delta will be the stocks 100, the puts -100. So the total will be 0. And that's what we mean by a delta neutral portfolio. And so if the stock goes up, we'll make money from the stocks and we'll lose exactly the same amount of money from the puts, and vice versa. So it's a risk-free position. So what we can do then, in a way, now think about it this way: what if we bought these stocks and we need to hold on to them for a certain length of time? What we've effectively done here is said, listen, we don't want to take on any more risk. Imagine that there's some reason why we're committed to holding these stocks until the end of the year. Well, what we've just done is created a risk-free position between now and the end of the year. What we're effectively doing is we're taking our profits out of this position. We no longer have to worry about risk. Okay. All right. Oops, what did I just do? Oh, it's asking me to save. I better save this. Hold on 1 second. You should never, I never trust technology ever for any reason. Everything I have is backed up like beyond belief. All right, that should do it. All right, good. So I can put this on Brightspace. Hopefully it doesn't. See, the thing is, even if it turns this one into a PDF file, it should still be fine. All right. So that's the put delta. Now, if you recall from when we did the Black-Scholes model, the Black-Scholes model only works for assets that do not provide any cash flows. Okay, what if they do? What if we're trying to price a currency option, for example? What if we're trying to price an option on the S&P 500? What adjustment do we have to make? All right, you recall we introduced this variable Q. Q represents the continuously compounded rate of return to the underlying asset. And that required an adjustment to the Black-Scholes model. Okay, let's go find it now. Here it is. This is actually sometimes called Merton's model because it was really Merton's idea to do this. You know, Black and Scholes and Merton, even after this paper was published, of course, they continued to do research. They were academics after all. And they all did interesting new things. For example, Fisher Black published a paper in which he explained how to price futures options. Merton decided to add this feature where you can now suddenly price options on assets that do provide cash flows to the owner. And assuming that the return to that asset is continuously compounded, we use the letter Q, and now we have to make two adjustments. We have this SE to the minus QT, and we have this minus Q. And what this does is it knocks down the price of the call because we're giving up the opportunity to earn this rate of return when we have a call instead of the asset. But it does actually increase the price of the put. So it does affect them both. Now, the interesting thing then is that if you're going to calculate Greeks from this model, the Merton model, we have to take that Q into account. So for example, with the deltas, instead of the one on the right, these are the original Black-Scholes formula. On the left, you see how we had to sneak in that e to the minus QT term. Now, e to the minus QT is typically a number that's very close to 1. It could be, for example, 0.9937 or something like that. So it's not a huge amount. And, you know, the Greeks are not necessarily going to be, they don't have to be crazy accurate. They just give us a sense of what the sensitivity is. So sometimes we see that these e to the minus QTs are left out because the thinking is that maybe they don't need to be quite that precise. But if you wanted to be consistent, you should incorporate those e to the minus QTs into those formulas. Okay, it's not that big of a deal, but the ones on the right and the ones on the left will give us very similar answers, unless Q is a huge number. But technically, this is what we should be doing. Oh, by the way, I forgot to mention, we did say before that the asset has a delta of 1. It turns out that that's also true of a forward contract. Just sneak this down here. So in other words, if you're hedging with a forward contract, hedging is easy. Very easy. And it turns out that they're both 1. I mean, it's also 1. Okay. So in other words, if let's say that to hedge a position in 100 shares of Apple, a forward contract would be entered into on 100 shares. Okay, hold on. Would be used. It would have to be exactly 100 shares because the delta would be 100. In other words, the stocks would have a delta of 100. So here we would actually be looking for a delta of minus 100. So what you would do is you'd enter into a short forward position, which gives you the right to sell 100 shares. And so the point of it is that you want the two deltas to exactly add up to 0. But the key detail here is that the number of shares in your contract would be exactly the same number as the position you're hedging, because the delta is 1 to 1. Now, if, let's see, we can draw another picture to show why that is. So when S rises by $1 forward contract, the value of the forward contract rises by $1 and vice versa. So yeah, the forward contract is a very simple instrument. So its delta, like the underlying asset, is also 1-to-1, or just 1. All right, now, what other fun things do we need to know? Oh, right, actually what I should have said, for a long position, it would be 1. For a short position, it would be -1. Okay, that's more like it. Yes. So in other words, if I own the stocks, I would buy a short forward position, and so the deltas would cancel each other out. That's always what we want. We want the deltas of the underlying position and the hedging position to offset each other. That's what hedging is all about. If they increase the delta, then I'm doing the opposite. Then I'm gambling. So the purpose of this hedging, overall, the purpose of hedging can be thought of as a reduction in the delta of a position. Okay. If you increase the delta, you'd just be gambling. Okay, so hedging means you're reducing the delta. All right. Oh, also, if there's a Q involved, then if the underlying asset pays a cash flow with a continuously compounded return of Q, then the delta of a long position would actually be not 1, but e to the minus QT, which is just a hair under 1 anyway. And the short position would just be negative, e to the minus QT. Okay, so you can think of the e to the minus QT as a type of present value based on the return to the asset. Okay. Now, here's one of the great things about this delta measure. It is what we define as a linear measure. No, we don't want to do that. No, exactly. We don't want to increase our delta. That would be counterproductive because we're just increasing our risk. You want to make sure that you're lowering your delta. So if you buy the wrong options for your position, you would know that you've made a mistake because your delta is going up. So remember, whatever your position is, like let's say your position is delta 100, you're going to have to go out and find securities that will lower that. So you might buy a put, or you might take a short position in a forward contract. Okay, always the goal is to lower it. It doesn't have to go all the way down to 0, but certainly you need to lower it below where it is now. And so here's the beauty of hedging with the delta is that delta is a linear measure. Now you can tell by looking at these graphs that we had, even though these are little tiny, look at these little slopes I drew here. These are all straight lines. The relationship between the stock and the option here, the delta has a linear relationship with the stock. Okay, so that means that the delta of an entire portfolio. Now we've seen a couple of examples of this already, where we had 100 shares of stock with a delta of 100, and we bought 100 puts, and that brought us to a delta of 0. The portfolio delta is just the weighted average of the individual assets. The W is the dollar value of that particular security. So you can figure out how many options or how many forward contracts you need, not only just based on their deltas, but because some of them may have different deltas, you may adjust the number of contracts that you buy or sell, so that when you multiply these deltas by weights or the amount that you own, you'll end up with whatever your desired hedging position is. I think I have a simple example in here. Oh, here it is. So we have $100 worth of stock X and $50 worth of puts. Their delta is -0.5. Okay, so what this means then, the stock has a delta of 1, and the, let's see, I think I'd like to expand on this a little. It needs a little more detail. So the portfolio delta so we just, formally write it out as the sum of the weights and the deltas. So I've got the stock the weight of the stocks is, I'll call that 1, 2/3. The delta of the stock by definition is 1. The put, 1/3 of my portfolio is invested in puts, and its delta is given to us as -0.5. So the portfolio delta is W1, delta 1, plus W2, delta 2, 2/3 of 1, plus 1/3 of -0.5. And so that's 2/3 minus 1/6, which I've run out of space. And algebraically, we know how to handle this. I can just rewrite this as 4/6 minus 1/6 equals 3/6, which is 1/2. Oops, 1/2. So even though it's not 0, it's still less than what it would have been if I simply held the stocks, which would give me 2/3. Actually, no, it'd just be one for each share of stock. So this is 1/2. So I've got a portfolio whose delta is 1/2. Okay. And delta neutral means the delta is 0. And this may be what I want. Maybe it's not, but if I'm really concerned about risk, this is something that I might think about. All right, it looks like I have another example here. We have 100 shares of stock, which means we have a delta of 100 from the shares. A put has a delta of -1/2. Oh, I think we already did this example. If I buy 200 puts that means 200 puts at negative 0.5 each would have a total delta of negative 100. So when I add these up, I do in fact have a delta neutral position. All right, so I think we get the point here. Now, what about all those other Greeks? What are they for? Well, we did see, now this was an important result. We did see earlier that when we changed the stock price, the delta changed too. All right, so when I changed the price of the stock by just $1, the delta actually went up a little bit because we're moving up this curve where if you notice as we increase S from left to right, this market price curve is getting steeper. And so it stands to reason that the deltas are going up. In fact, why don't we try this? Let me try 62 and see how high it goes. So that brought the price of the option to 0.0222, and the delta went all the way up to 0.8248. Yeah, look at that. And that's because we're moving progressively deeper into the money. In fact, if I put this up to a ludicrously high level, like 92, the delta is almost 1. Look at that. Because the chances of finishing the money are almost 100%. Okay. And remember, on the expiration date, either we have a delta of 0 or 1. When we're on that red line, either we have 0 or 1. There's nothing else to choose from. So this actually reflects the likelihood that we finish in the money. Very high delta means it's almost a done deal that we're going to finish in the money. A very low delta would mean the opposite. Anyway, because the delta itself can change when S changes, which, by the way, can be a problem for hedging, because if there's a significant change in S, your delta neutral portfolio suddenly is no longer delta neutral. Now that's a real headache. Okay, in other words, if the deltas are changing, then my position is also changing. So the trader has to keep an eye on this. They have to make sure that the delta, the portfolio is still delta neutral after a change in the market. So the next Greek that we're going to look at, which is called gamma, tells me how sensitive the delta is to changes in the stock price. That's an interesting question. You saw for yourselves that when S goes up, so does the delta. The question is how much. That's what the gamma is trying to capture. And this is an important measure for hedgers, as you can imagine, because like I said, if the delta is changing, then your position may no longer be delta neutral if this is what you wanted. So how is this gamma defined? Well, first of all, the uppercase gamma is this thing. It looks like a 7, basically backwards 7, okay? The gamma that you might be more familiar with, hold on a second. Is this one on the right. It kind of looks like, I don't know, like a big fish. You may have seen this one before. The one on the left, the backwards 7, I guess, is your uppercase gamma. By the way, all we have to do is go look at Wikipedia. All right. Yeah, maybe I'm not drawing it as well as I could. It's got the one on the left is the uppercase, the one on the right. It's kind of fishy looking, is our gamma. And if you really want to know more about it, here it is. I don't know. I think it's enough to know what they look like. So the gamma is the sensitivity of the delta with respect to the asset price. Oh boy. Now it's getting complicated. This is the first time we're seeing a Greek that is actually a function of another Greek. Now, as you can probably imagine, the put gamma is defined in the same way. The change in the put delta with respect to the asset price. Now, here's the interesting part. In order to visualize what this looks like, here's what we can do. Let's go back to these graphs. This is the call delta. The gamma can be obtained by looking at how these slopes change as S changes. So what you're effectively doing is looking at the changes of those slopes. And if you notice, the slopes are rising quickly, they're flattening out, and then they're dropping. So we're thinking not about the absolute values of these slopes, but how they're changing. So the graph that results from this, let's go look at it. Hold on. There it is. This is what the final result looks like. And if you notice, it's like a mountain, basically. So if you notice, the gamma is never going to be negative. Okay, because as the stock price goes up, the delta, while it may increase at a progressively decreasing rate, it never actually decreases. So it peaks out right around the strike price, right at the money there. So just the two things to note is it's never negative, and it should reach its peak when we're right at the money. But also, if you look carefully, I know it's a very small thing to see, but if you look at the axis, these numbers are actually quite small. This one on the top is 0.03. It's a very small number compared to the delta. And unlike the delta, there's a lower limit to the gamma. There's no upper limit to it. Okay, all we know is that it's got to be either 0 or positive. Now, let's go back and revisit that graph of the call delta and look at the corresponding graph for the put delta. And if you recall, they have the same shape. The only difference is that one is negative and one is positive. And because the gamma refers to the changes in the deltas, because the curves have the same exact shape, it turns out that the call and the put option with the same features, same strike, maturity, and underlying asset, always have the same gamma. In other words, it's identical whether this is a call or a put. So we don't need a separate graph for call gamma and put gamma. So in other words, this graph that I just showed you is actually for both. It doesn't matter which one it is. This gamma refers to both calls and puts. Now, this is not the only Greek where this is true. We'll see later on that there's another one that behaves like this. But it's kind of strange to think about it. They both have the same gamma, exactly the same, as long as they're the same themselves. And so these gamma numbers are very small. And that's because the slope doesn't change that much when the stock price changes. So how do we calculate it? Well, this one's a little bit messier. We're going to need to lean on a function in Excel, which refers to the rate of change of this normal curve. So let's say this is D1. This n prime of D1, instead of showing us the area to the left of this, which is what our delta does, this one is referring to the height of the curve at D1. So it's called in the book n prime of D1, as opposed to just plain old n of D1. N prime of D1 means how high is the curve at that point. It basically refers to how much the curve changes at that point. And if there is a dividend yield, then we need this. So it's not a very complicated function. How do we calculate it in Excel, though? All right, let's take a look. And let's see what kind of numbers it gives us. Looks like I must have done that on the next page. Here we go. Oh my God. So on this page, I've got the formulas. Look at them all. Here's my call gamma and the put gamma. They're both exactly the same. And how is it done? Wow. Okay. So if you compare, let me go get a copy of this formula for us. See where I can sneak it in here. I got so much good stuff going on here. So you can see what I'm, well, here it is. Now this one, I just realized this one doesn't have the e to the minus qt part. Norm.s.dist is this n prime of d1. The denominator is s times sigma times the square root of t. So this one is missing that part. But if there's no dividend yield, which there isn't here, then it obviously doesn't make any difference. But that's how it was done. So just remember, norm dist is the normal distribution. Norm's dist is the normal distribution. Norm. Oh, wait a minute. No, I'm sorry. I said that wrong. Here we go. So here we go. Note. Norm.s.dist can be used for both nd1 and n prime d1. What is different is that with norm.s with nd1, we use norm.s.dist d1, and then we need to give it a value 1. The second value is 1. Okay, in fact, if you see here in nd1, that's exactly what happened. Oh no, you know why? That's the older version of the norm dist. Let's try this. So in other words, you're supposed to tell it the value d1, and then you need a 1 to indicate that this is in fact n of d1. When for n prime of d1, we use norm.s.dist, but then it's d1 comma 0. Okay, so that's how you know the difference in Excel. That second value, the 1 means it's n of d1, which means the call delta. If we want n prime of d1 for the gamma, we need to change that 1 to a 0. That's how Excel does it. Okay. Okay, this is notation Hull uses in his book. But graphically, like I was showing you, this one means the cumulative area to the left of D1. This one is simply the height of the curve at that point. It is not a cumulative probability at all. It's a rate of change. Okay, so if you know, that's hopefully that'll be helpful. Okay, so the gamma, now, by the way, the gamma is very important in the trading strategies because now if you're concerned that you set up a delta neutral portfolio and yet the position changes very quickly, what you can actually do is make your portfolio both gamma and delta neutral. And that means you're guaranteed that even if the stock price changes by a lot, the delta will be forced to stay in its right around where it is now. The only problem with that is that you now need at least 2 hedging instruments. Okay, and so it gets a lot more complicated. It can be done, but in order to keep the portfolio both delta and gamma neutral, you must now have 2 different hedging instruments. Now there's 2 different options, or maybe 1 option and 1 forward contract or something like that. And they have to be the right values so that the gammas and the deltas all add up to 0. All right, so it's getting very messy now. Oh, one more thing. I almost forgot to mention this. We saw earlier that when it comes to delta, let's just quickly summarize what we know about delta. The delta of a stock is just 1. Or the delta of a long forward position is 1. The delta of a short forward position is -1. The delta of a call is ND1. The delta of a put. Okay, so when it comes to gamma, the gamma of a call or a put option is, and then it's just that formula that I showed you. All right, let me just copy this in here real fast. Here we go. But it turns out the gamma of a forward contract or a stock is 0. So what that means then is that if you're interested in simultaneously becoming delta and gamma neutral, one of the easiest approaches would be we can use a forward contract to become delta neutral. And then we can use an option to become gamma neutral. As long as we don't, choose the wrong values, of course. So in other words, you can actually create a position where you're altogether both gamma and delta neutral by using the appropriate mixture of, let's say, a forward contract and an option. Okay. All right, well, this is getting to be a bit complicated. So why don't we move on to the next of our Greeks? But you can see why this is so important. This is not just for academic curiosity. I mean, it's fun and all, but really it has a very serious purpose in the options markets. And of course, you can also use these Greeks to try to do the opposite, to take exposure for speculative purposes. You could actually add, like I was saying, add gamma or delta. Yeah, yes, I made sure, you know what I did? Because I saved it for that very reason, so I don't lose it. Because yes, there's a lot of useful stuff in here. Yes, definitely. All right. So what I wanted to say is let's go on to the next one, which is theta. Now, the mere fact that it starts with a T sort of is a clue that this is the one that tells us how sensitive the options price is to changes in time. Now, this is an oddball one because time can only go one direction. You know, the others, you know, the stock price can go up or down, you know, the interest rate can go up or down, volatility can go up or down. Time is different. It can only go one direction. Now, here, what we're specifically referring to is how much does the options price change? No, well, actually, sorry. The time value of the option changes as we get closer to the maturity date. Okay, so in other words, and we've seen this before. Let me just quickly remind you, let's say for a call. Here's the payoff, intrinsic value. Let's say the market price with 6 months to maturity. And then after 3 months, well, anyway, you get the idea. And then with 1 month to go, you might find it looking like this. It's going to get closer on the actual final day of trading. It will coincide this market price line with the payoff profile. They'll be identical on the final day of trading. So what's happening is that if there's no movement in the price of the stock, you're still losing. Okay, so as time elapses, with no changes in other variables, the intrinsic value doesn't change. The time value shrinks, or specifically say decays. Okay, and will equal 0 on the final day of trading. So the theta measures how fast the options time value is decaying. That's all it does. It says, listen, how fast are we losing money due to the passage of time? Okay. Now, because the time value is always positive, options that are deeply out of the money will have a low theta because there's little value to lose. Options that are deeply in the money will have a higher theta. But it actually will behave differently than you might imagine. It turns out, though, that the highest thetas are actually those at the money options. That's where the time decay is the fastest, because most of the value is the time value. Let me see if I can draw a proper picture of this so you can see why this must be the case. Let's say, okay, I can live with this. What I'm trying to get at here is that at the money, the entire value of the option all of the options price is time value. It's all time value. Okay, now that's true here too, but there's little chance, less chance of the option finishing in the money. So that means that the time value is not as sensitive as it would be for the at the money, which is, think of it as sitting on the fence between finishing in and out of the money. So there's some time value there and it will decay, but not very rapidly. Because there's, very little, not very much chance that the option might actually finish in the money. And of course, up here, these are deeply in the money, a small percentage of the option's value is the time value. Most of that is the intrinsic value. Okay. So that's why this is the one that's going to change the most when time elapses, because so much of it, it's essentially all time value, but it's also, there's a real chance that the option could finish in the money and the value could continue to increase. So that means that if it moves into the money, a lesser amount of it is time value. A lesser amount of its total value is time value. So if you look at the graphs that are created, and by the way, these formulas are terrifying because T appears so many times in the Black-Scholes model. Yeah, so this is what I was referring to. Now, this is a call theta. And so here we're at the money. Here we're in the money. And here we're out of the money. So you can see that as we move further into the money, at first there's very little change. And then, whoa, look at that. The time value falls off very dramatically as time elapses, and then it starts to level off and starts to shrink again. But if you notice too, those are all negative numbers. The negative means that the value is decaying. By the way, I've been informed reliably by people who work on Wall Street that because people are so averse to negative numbers, when you see, if you went to a brokerage house and asked for a report of some kind, and they showed you all the Greeks, the convention appears to be to ignore the negatives because it's understood that it's going to be a negative number. So therefore, don't be surprised if you've got your hands on a printout from Goldman Sachs showing options positions. I don't know, I'm not sure if this is such a smart idea, but it'll show them all as being positive because it's understood that they're really negative and people just don't like negative numbers. So that's, I just wanted to mention that as an aside, because, they're all negative, but people hate negative numbers. So when you see a positive number, it's understood that that's what it means. Now for the put, you can see it's got to be, we have to reverse this from left to right because now this is at the money. This is out of the money. And this is in the money. So from left, if you could go back and forth between the two, they're mirror images of each other from left to right. Okay, but by the way, the numbers are not necessarily the same. They're similar, but they're not identical. The formulas are not the same. So in other words, unlike the gamma, the call and put thetas are different from each other. You do have to make a distinction between them. Now, if you, by the way, you could actually show how this changes over time. Let me just quickly sketch what that would look like for you. Actually, let's do gamma here. Or actually, let's do delta. Now, this one could be a little confusing because this 0 means the expiration date. And this could be, for example, today. What happens here is that as time elapses, on the final day of trading, the option has to have a delta of 1, no matter where it started out. So this is an in the money option. This is at the money, and this is out of the money. And what it's trying to show you is that no matter what the deltas are now, by the time the option matures, and in the money option, a call, that is, I should say, call, will have a delta of 1, and at the money call will have a delta of the half, and out of the money call will have a delta of 0. Okay, so in other words, they do change over time. And they do have to converge to one of these 3 extreme cases, 1, a half, or 0. Okay, and you can kind of see why. Because remember, what's happening is that the market price is converging to the intrinsic value. And so, as that happens, oops. We might start here, and then we get closer to here, and then at some point we end up here. Okay, so there's only 3 choices: a half, 0, and 1 on the final day of trading. All right, anyway, so there's our theta. And yeah, the formula is just horrendous, but you know what, in the spreadsheet here, I have typed in the formulas for you. So if you want to know, given this initial starting values, all of them are here. I did plug in all the formulas. Oh, you know what else I wanted to mention too? Sometimes what you see on Wall Street is that this theta is actually an annualized number. What you'll often see is they'll just take this and divide by the number of trading days in the year, which is assumed to be 252. And this becomes the daily theta. So it appears that this option is losing about 1.3 cents worth of time value every day that elapses. Because I guess the traders find that to be a more meaningful value than the annual number, which is what you're seeing here. So that's the convention. Just divide by not 365, because the options don't trade on the weekends, but 252, because that's the approximate number of business days in a given year. And so you end up with a daily value instead of an annual value. Okay. It depends on the trader, I guess, which one makes the most sense, but it's a common practice to express these on a daily basis. Okay. Anyway. So, but the scary looking formulas, they're up here. If you want to look at them, look at this formula for the qual theta, by the way. Oh my God. It's a nightmare. Okay. But that is what it looks like. Well, all right then. Now I think it turns out, now this is kind of an interesting, Paul mentions this in his book. It turns out that you can actually calculate the change in the value of your portfolio over a given time interval by actually combining these Greeks. In other words, given this information, the implied change in the value of your position is this. Okay. I don't know how that's going to help us, but it does show that these are tied together. If we combine them in the right way, we're going to end up with the risk-free rate of return for this portfolio. Now, we're ready for the oddball one. This is the one that's not even a Greek letter. It's Vega. Now, Vega, as you may know, is actually a star in the constellation Lyra. It was chosen apparently because it starts with a V, which is the same as volatility. But because we don't have a letter associated with that, the one that is often chosen is lambda. Okay, notice you have to write something down. This is the Greek letter lambda. Okay, sometimes you actually see it written as kappa as well. Okay, but remember, they all mean the same thing. This represents the change in the value of your option due to a given change in the volatility. Okay, so it's a sensitivity of the call price due to a given change in the volatility, or you could write it more precisely as delta C, delta sigma. Remember, sigma is what we mean by volatility. Okay, and this is, by the way, an annualized number. Now, we did mention this once before. Volatility is beneficial to an option, whether it's a call or a put. The issue here is how much does a change in volatility add to the value of an option? So what this implies is that this call Vega has to be positive. All right, and we'll prove it in a second when we see the formula. Now, the equivalent version for the put is right here. So this is the change in the put price with respect to the volatility. Now, if you go to the Black-Scholes formula, you'll find a very interesting result. Just like with the gamma, the delta is the same whether it's a call or a put. Interesting. Now, also here we can see why this thing has to be positive. Because remember, n prime of D1 is simply the height of this curve at D1. Okay, so we know that term is positive. We know that T, the square root of T is positive, and we know that S is positive. So this term is guaranteed to be positive. So in other words, volatility can only help the value of a call or a put. And it's the same for both calls and puts. All right, the fact that it's a call or put does not affect the impact of volatility on the option's price. And you notice how it's a very simple formula. In fact, it's right here. What you're doing, actually, let me make a copy of this formula for a second. So I can sneak it in here. Maybe right about here. So we can compare that with the Excel formula. Now, this is, remember, we had this earlier, this n prime of D1 means you're using this norms S disk function with a parameter of 0. But you're also, then once you have that in place, all you're doing is multiplying this by the stock price and the square root of time. Okay. So that's your call. But you notice how the call and the put are both the same. In fact, if because they're the same, I just typed in here equals B28 because they're both the same thing. So what does this number actually mean? 19.53, how do we interpret that? So yeah, this is just what I did here. It's the same example. And so these are all the other Greeks, they're all here. And so what we want to know now is, what does this number mean? All right, so the way we interpret it is this. A 1% increase in volatility adds 19.53 times 1%, or 19.53 cents to the price of either a call or a put. Okay. So that's a little bit of an interesting one. You might not have thought that that's what it means if you looked at it the first time, but it just says a 1% increase in volatility from, let's say, 20 to 21% per year is going to add roughly 19.53 cents to the value of the option. So we can try an experiment here. Let's see. What I could do is change signal from 30 to 31. So according to this, the prediction is about 19.53 cents. All right, let's see, where can I hide that? Oh, it's already here. I forgot. All right, here we go. So I've already done it. Look, so here are the Vegas with a 30% volatility. These are the prices. So when the volatility went to 31 cents, the prices predicted, you can see they're almost identical. The predicted and the actual are nearly identical to each other. So this one does a very good job. Now, the call delta and the put delta are a little bit more inaccurate because they're linear measures, and the option price itself does not come from a linear function, but the volatility is not linear, and so the approximation is improved as a result. So you can see they're awfully close. It's almost perfect, as a matter of fact. Now, what about the graph? Let's take a look at this thing. It's the same for both of them. You notice how it reaches a maximum value when the options are at the money, and then it sort of tails off in either direction. It can never be negative. But one thing that's different with the gamma, which, if you notice, the shape is very similar. Let me just remind you what the gamma graph looks like. It's almost the same. Look at that. Very similar. But if you notice, the gammas are very small numbers, whereas these vegas are really large. In fact, this one can go up as almost up to 20. Okay, so other than that, they look very similar to the gammas. So basically, if you think that the market is about to head into a period of turmoil, this will give us a sense of how much your options positions are likely to benefit from it. And you can see again where hedging could be so important, because if volatility is going to hit the markets, your stocks are likely to lose ground, but your options are going to make some money. So you might hold options just for that reason alone, because you really believe that the market is heading into turmoil, and any options you own will benefit from that. Even like, no matter how you set them up, whether you have calls or puts, the options that you own will benefit from that. So this is a huge deal. And in fact, there's no other hedging securities available that can let us hedge changes in risk, volatility rather, okay? Because they're linear instruments. So there's forward contracts cannot hedge against the risk of changes in volatility. They can only change or hedge against the risk of the underlying asset price. But here we now have the ability to hedge against the risk of volatilities changing. And I think I already mentioned this once before. If you're really interested in hedging volatility, you can actually buy an option on the so-called VIX index. And let me just show you a graph of this thing. The VIX index, by the way, now that we've studied options a little more, the VIX is based on the implied volatilities of Standard & Poor's 500 options. And so when the market goes into turmoil, like it did during the COVID, of course, the volatilities will spike up. Look at this, it got up to 82.69%. When, you can see that a more normal level is about 33, 31, 20 even. And then prior to that, during the housing crisis, the VIX got as high as, only 40 or so, but these bars represent essentially recessions, and you can see that they do spike up. Sometimes they'll spike up even if the economy is very strong, but that would typically indicate there's something else going on, some kind of international turmoil. But if you really want to protect yourself from volatility, you can actually buy an option on the VIX, which will a call would benefit from rising volatility, and a put would actually lose money if volatility goes down. Wow. Okay. So the VIX index has an interesting history. It was suggested to this exchange by a professor at Duke, Robert Whaley. He always wondered why there wasn't a VIX index, and he talked to them about it, and he told them he thought it was a great idea. He finally convinced them to create this thing, and it turned out to be extremely successful. A huge deal. It really makes it a lot easier for traders to hedge their positions. I don't know if there's any futures contracts on the VIX. Let's find out. Yeah, there it is. CBOE mini VIX futures. So I guess that answers that question. So no, you cannot buy directly into this index, but you can get futures contracts, also exchange traded funds. Basically, those are collections of stocks that are designed to replicate an index. So you can actually own a set of stocks that will benefit directly from changes in volatility because they've been set up for us. But yes, but you don't need this index to protect yourself from volatility by owning options. All right, anyway. So now, and of course, as always, in all these cases, if the asset underlying our options has some kind of cash flow, then we need this at e to the minus qt term. Okay. Now, there's only one more. Now, this is a strange one. Rho. In fact, if you notice in the Wikipedia article, they didn't even mention it because it's really apparently not as directly useful as some of the other ones. And what we're trying to capture here is what happens to our option prices if there's a change in interest rates. Okay, so let's go back here. Look at our list. So yeah, that would be the last one in our list. Rho, which this is our Greek letter rho. Usually you see it in statistics used to describe correlation. But here, I guess it was chosen because it starts with an R. And so here what we're referring to is how sensitive is our options price with respect to changes in the risk-free rate of interest. In other words, a treasury bill whose yield on a treasury bill whose maturity matches up with our option. Now, part of the reason why this is less important is because interest rates are just not that variable over time, not at least compared to some of these other measures like volatility. over, most options have a very short lifespan. Let's say 6 months or less. And during that time, interest rates may not change at all. So there's a lot less need to hedge the impact of interest rates on our options. But it's still an important measure to be aware of. And so what we're trying to capture is if there's a change in the risk-free rate of interest, what would that do to our option price? Now here, the reaction of calls and puts to changes in interest rates is very, very different. And in fact, it turns out that higher interest rates will benefit call options and will reduce the values of put options. So what exactly is the reason behind this? All right, so let's say that let's say that an importer needs to buy, or it doesn't even have to be an importer. Let's just say a manufacturer of jewelry will need to buy gold in 6 months. There's some reason why they must buy more gold in 6 months. They have some contractual obligation to produce a certain amount of gold, and they know that they'll need to buy more gold in 6 months. So in order to hedge price risk, the manufacturer can buy a call option and pay for the gold in the future, or buy the gold today. So now, of course, which one do we use? Well, the first choice means that we can postpone payment for the gold for several months. The second choice means by financing the purchase of gold today. So the first choice will be more valuable and save more interest as interest rates increase. Okay, so in other words, you're giving up, you don't need to buy the gold right away and use an option. So that means you don't need to use your own funds today, or except for the price of the option, of course, which is a small percentage of the value of the gold. So you're basically postponing the time in which you have to pay for the gold. So therefore, the higher the level of interest rates, the more valuable the call is. Okay, so the higher the level of interest rates, the more valuable will be the call option. Now with a put, suppose that a mining company plans to sell gold in 6 months. In order to avoid price risk, two choices are buy a put, which locks in the price at which delivery takes place in the future, or sell the gold today. Now, if the gold is sold today, the proceeds can be invested and earn interest. With a put, the ability to do this is postponed for several months. Therefore, if interest rates rise, this reduces the attractiveness of buying the put. Compared with selling the gold today. Therefore, as interest rates rise, the value of a put declines, and vice versa. So, with all that being said, this means that the row of a put call will be positive. The row of a put will be negative. So they have to go in opposite directions. All right. And so anyway, when you see the formulas, you'll realize right away why this is happening. Again, you can tell just by looking at the variables. For example, here, this is the formula for calculating the row of a call. And you can see for the first time we have ND2, by the way. We haven't seen that before. But ND2 is a probability, so this has to be positive. The strike price K is positive. T is positive. E to the minus RT is positive. It's a number slightly less than 1, and N of D2 is positive. So because all 4 of them are positive, this guarantees that the row is also positive. Okay. ND2, if you recall, is basically ND1 minus a constant. Well, that's interesting. Now let's look at the equivalent for the put. And there you go. See, now this value is also, since it's a probability, even though it shows a negative here, this has to be a positive number. And all of them are positive, except, and then we have this negative sign on the outside. So therefore, this is negative. But just as we expected, they're going to be of opposite signs. They have to be. All right, so the example that we have here in our spreadsheet, same one, I'm using the same one throughout, the same option. The puts, they're right here, the call and the put row. By the way, if you notice, they're not just the same number with a different sign. They are actually different. But the important detail is that the call row is positive and the put row has to be negative. So the big question here is, how do you interpret this? What does that even mean? Well, let's see. The call row means if interest rates go up 1%, then the price of my option should go up by 1% of 25.43, which is 25.43 cents. Okay. Now for the put, we have the opposite, negative 23.58, which means that the price of the interest rate goes up 1%. The price of my call, my put rather, should go down by about 23.58 cents. Now, if you notice down here, I did the same experiment. And what I did was I showed what the rates are here, what's everything today, the initial values from our problem. And then I allowed the interest rate to go up from 2 to 3%. I calculated what the price predicted would be from the row formula, and the actual I calculated by simply changing the interest rate over here. And you can see the differences between the call and the put predicted values are very, very trivial. So this one, you know, it works really well. If you go back up here and you look at the same thing for theta, man, those are close. These are really close. The only ones that are a little bit off. Yeah, the calls, the deltas can be a little bit off. But again, remember, delta is a linear measure. And so it stands to reason that it's going to be more inaccurate than the other ones. So yeah, you can see already, even with a change of $1, the delta is off a bit. You know what, let me just see if I can draw a little picture that shows you why this is happening. Because here's what you're trying to do. You're taking this price curve, you're saying, all right, and here's my market price curve. If I started here, for example, call that S1 and here's S2. Oops. Yeah, that was terrible. The call price here, I'll call it C1 and C2. Using the delta to predict the new price means here's what you're actually doing. I'm defining a straight line. Okay, so in other words, what you're seeing here is the predicted C2. Using the delta measure, because I'm using a straight line to approximate a curve. That is the holdup right there. Right there is the problem. So you can see the predicted is too low. And so you can see here, same thing, the predicted call is too low. And if you reverse this from left to right and use a put, it'll be the same thing. The predicted put price will be a little bit too low. Okay. So again, it's because of the fact that this market price curve is a curve, and the delta itself is the straight line. It's the slope of the curve at a single point. That's where the inaccuracy comes from. And what that means then too is that as the change in S increases, the inaccuracy also increases. For small changes in the stock price, the predicted call price will be reasonably accurate, but not perfect. Okay, so this is a common, you run into this when you're using linear measures to approximate nonlinear measures. Oh, you know what that reminds me? This really drives me crazy with Microsoft Word. The default case is not to have page numbers. That really is annoying. With such a long document, there'd better be page numbers. That's the way I look at it. I don't want to flip through these and look for certain pages if they're not listed here. Okay, that's better. Okay. Now, the Greeks will show up again. Oh, you know what I did here? I put together a little table. I do want to mention that there's a couple of very bizarre cases involving European calls, where if they're under certain very unusual conditions, it's possible for the theta to briefly become positive, but it's an extremely unusual case. It's almost not even worth mentioning it. But other than that, the theta is always going to be negative across the board. So this little chart is trying to show us when the impact is positive and when it's negative. And so you can see that, of course, it's the same for vegas across the board. Always positive, always negative. Oh, one more thing I just wanted to mention here, and I guess we didn't talk about this. Selling an option reverses the sign of the trader's position. For example, if a call on Apple stock has a delta of 0.5, let's say, the seller of the call has a delta of negative 0.5. Okay, so just be aware of that. All of these positions that we talked about assume that we are the owners. If we're not, if we're the sellers, then everything works backwards. It's always going to be the negative. Okay, so buying and selling have to have the opposite signs when it comes to the Greeks. So yes, as I started to say, the subject that's coming up next week, which is sort of tying everything together, is this concept of what's called, well, the field of risk management. And really options are part of this, because what you're trying to do in risk management is figure out the best way to hedge your risks. And really that's the bottom line. And so this field has its own unique statistical measures that we can use, but we can apply all of these concepts to options. And again, we will see that we can measure and manage a risk with this value at risk framework, it's called. And some of the calculations do involve the Greeks. Okay, so the Greeks will show up in this discussion as well. So again, they're not just there for academic curiosity. Oh, I almost forgot one more thing. I mentioned with the thetas that these are usually simplified to a daily number. With the rho, no, I guess not. The rho is usually not. Oh, I know what I forgot to show you. The graphs. This is the graph of how call rho behaves. You know what? I don't know enough about what happened with Credit Suisse, but I am sure that poor risk management practices contributed to it. The thing is, you get a lot of these crises, and it turns out that these people were taking ridiculous risks. Like you might remember that Bear Stearns and Lehman failed during the housing crisis because they were rolling the dice with these newfangled credit derivatives where they really didn't understand how badly things could go for them in a hurry. So even if they had used proper risk management techniques, the instruments were so new that nobody truly understood how sensitive their prices could be to changes in market conditions. And so when things started going badly, it all fell apart at the same time. And so all of these instruments, which they believed were hedging their risks, were actually doing no such thing. And also it didn't help that the credit rating agencies like Standard & Poor's and Moody's were assigning high credit ratings to these products that turned out to be basically crap. So this situation, I'm not sure if it is due to, well, why don't we find out? But I can pretty much guarantee you that whatever they were doing, it involved poor risk management techniques. Although sometimes that is the direct cause, and sometimes it's because of other reasons. Credit Suisse, I remember seeing this, the UBS was buying out Credit Suisse, but unfortunately I did not read the article which explained what happened to it. So, you know, that SVB Bank was apparently taking positions that were contrary to the interests of their stockholders, just so they could be politically correct. What did they do here? A subtle, oh, here it is. So UBS chairman highlights his bank's conservative risk culture. There it is. A subtle swipe at Credit Suisse's reputation for more swashbuckling, aggressive gambles in search of bigger returns. Okay, so he's basically saying it right there. He thinks that their risk management practices definitely contributed to this. but it doesn't explicitly say how. That, yeah, I guess we'll find out in the days to follow exactly what was going on here. They must have, wow. It says here they do not overlap with the weaknesses that brought down Silicon Valley and Signature, whose failures led to significant rescue by the FDIC.
Just
Yeah,
just a
unfortunately, it's not giving us any lead.
just a quick comment, quick question. Some of the people, on the radio are speculating it has something to do with interest rates, that there was a rapid rise in interest rates. Could it be like they're guessing wrong if they're doing like interest
Yes.
rate futures and derivatives?
Yes, it could. Absolutely.
And
They may.
I was just wondering just
gamble-
if you could comment on why you think they would guess wrong if they were forecasting rises in rates for like a very
Well,
long
it may
time.
be something as simple as not anticipating how quickly interest rates would go up. They may have realized that they were going up, but maybe not quite as high as they go. Now, what often brings these companies into trouble is that when they take their positions, they're not just buying, let's say, the wrong futures contracts, which doesn't help matters, but they may be borrowing a lot of money to leverage their positions so that you're basically buying risky securities with borrowed money, and that just makes things 10 times riskier. And that often turns out to be what the problem is, that they essentially were rolling the dice, but in such a way that if they were wrong even by a little bit, they would lose an enormous amount of money. See, maybe there's some details here, but yeah, you can rest assured they guessed wrong. They gambled big on positions that turned out to be incorrect, and they just were too aggressive in the way they gambled on these positions. How did it collapse so fast? All right, maybe this will. Fortune is a good source. Now look at that. This is another thing that drives you crazy. The so-called banking regulators looked at their books and said, yeah, you're good. So that means they missed the boat too. They overlooked something, maybe deliberately. Credit Suisse had to be bought out, $3.2 billion deals brokered by the Swiss government from UBS. Well, you see, the other thing that happens here is that a place like this, Credit Suisse, starts to get the attitude that we're so big and so important that even if we roll the dice and it goes badly, don't worry, the government will bail us out. It has to, because otherwise so many jobs will be lost. And they start to have that mentality that they are going to be protected from their own stupidity by the government. And that's been the root cause in a lot of these failures. Let's see. Oh, so when they start to lose money, they have to sell off assets to raise funds. And then people take their money out of the bank. Depositor flight. Yeah, because you've got to have people's money to lend out. And if you start to lose confidence in the markets, people can take their money out. And before you know it, well, you've got to start selling your assets, probably at a loss. But still, no, they must have been doing something that was heavily leveraged and risky. I mean, this is not normal. Banks survive these types of crises all the time. No, something else is going on here. Yeah, they must have done something with the derivatives markets. It says here that the UBS chairman indicated these were not toxic assets sitting on the balance sheets, which is what was happening during the housing crisis. They would be sold off. So they're starting to blame it on the long period of zero interest rates that encourage excessive risk taking. There's an important difference. In 2008 crisis, we had opaque, hard to price assets like collateralized debt obligations. This involved mortgage providers originating loans with little regard to the creditworthiness of the client. They were then bundled together into securities such as collateralized debt obligations, which were given high credit ratings, which were not warranted at all. When housing prices started to collapse, the whole house of cards came down. Most of the assets held by Credit Suisse and SVB are standard products like treasuries. Oh, so they're blaming it on partially, at least on bank runs. How do you like that? But that's surprising. You wouldn't think it could get that bad in such a short period of time. Right. So the central bank, has to step in. If these were not Swiss banks, the Fed would have had to step in and provide liquidity to all these banks and provide reassurances to the markets that this is not something that's going to be spreading throughout the entire banking system. So in this case, it's the Swiss central bank that's on the hook. But even it says here, the Fed, this European Central Bank, and 4 other major peers agreed to provide dollars on a daily rather than a weekly basis. So they're basically going to pump up the banking systems by saying, here, if you need money, take it and pay it back when you can. So, I mean, it looks like they weren't being maybe necessarily very irresponsible with derivatives, but they must have been doing something to lose people's confidence so quickly. This is very strange. This is kind of new territory because in the past, most of these crises in the last 40, 50 years were because somebody was doing something they shouldn't have with derivatives, which led to massive losses in a big hurry. Here, it doesn't really look that way. It looks like it's more about confidence. Very strange. Wow. Makes you wonder. Huh. Well, anyway, so we'll see how this goes, but luckily it shouldn't affect the US too much. But and so in risk management, they spend a lot of time studying these past crises to make sure that they learn lessons from it. In fact, I actually have this certification called FRM, which stands for Financial Risk Manager. It's a standardized exam given out by GARP, which is the Global Association of Risk Professionals, and they had us studying a lot of these cases from the past 40 years to examine what happened to cause all these failures and what could be done about it. So I'm very familiar with a lot of cases from the 80s and 90s and the early 2000s, but I haven't needed to study them recently, but this is definitely one of those cases where we all want to know what happened. And so it'll be in the news quite a bit over the next few weeks, and we should all pay close attention to these articles to see maybe other things were happening that we didn't know about, but this is new territory. You don't normally see banks come close to the brink because they've lost confidence, because usually the investors wouldn't even know that something was wrong. So I guess that wasn't true this time. So, all right, anyway, so I guess we've had enough fun with the Greeks. So there's no assignment this week. Next week, we'll wrap it up with our look at risk management and risk management techniques and the value at risk framework, which will help us see how you can tie together all of this and try to understand how you can reduce the risk of a portfolio. And then, unfortunately, that's it. We'll be done. I don't know if the school is ever going to have any more advanced derivatives classes, but I think we covered a pretty large chunk of Hull's book. And so hopefully this will help you with your other classes. So I guess I'll just see you all next Monday then.
Thank you. Thanks. Have a
Thank
great
you.
night.
Right, good night,
Good night.
good night, everyone.